This is a topics that I think it has a most subtopics as compared to other topics. Okay, so my main reference is control system engineering, Norman S. Nice. So you can refer to the books if you have any trouble understanding my lectures. All right, so next one. Uh, this is the CO2. We have covered CO1 in the previous class. The CO2 is the ability to perform system response analysis and stability in time domain. Okay, we will cover two types of systems. First order system, and then we will cover second order system. A higher order system, meaning that third order system, fourth order, fifth order, sixth order, and so on, will be also analyzed using the second order system that you will learn shortly. Okay, this is the first one is the first order system is a very simple one, because you will have only plot something like this. Okay, remember last time you learned about the example of what we call it the elevator. Okay, the elevator. So you will have the transient response, and you have the steady state steady state at the end of the response. Okay. Okay. Next one. This is a chapter learning outcomes. Um, what you will learn in these topics is you will learn about the how to determine poles, how to determine zeros from the transfer function, uh, and from these poles and from these zeros you can be you are able to determine the time response of the control systems. And then next is the describe the quantitatively the transfer response of the first order system. Okay, and next is you will learn how to write the general response of the second order system given the pole location as well as the zero location. And then after that, you need to find the damping ratio, natural frequency of the second order system. And then we will use the parameters for the second order system, such as cycling time, peak time, percent overshoot, rise time for the underdamped second order systems. And then next one is when we finish learn about the second order system, we will try to use we will try to analyze the higher order systems and system with zeros with the approximation to the second order system. Okay. Okay. The first one is to identify poles and zeros of the transfer function. So previously I have shown a few examples of the transfer function. So the transfer function can be you can identify the numerator and denominator. So this is numerator. Okay, numerator. This is the denominator. Okay, the numerator and denominator. This is numerator. This is denominator. So this numerator is called the zeros. S plus 2 over here is called zeros. S plus 5 over here is called poles of the transfer function. Okay, so numerator zeros, denominator is poles. Okay, so when we plot on the S-plane, so we have this S-plane. When we plot, we will represent the poles as the symbol X over here. Okay, symbol X. This is poles, and we have our zeros represented by the symbols of circle over here. Okay, y -5, y -2. So when you put it on the S-plane, so we have our zeros is S plus 2. So basically, when we put on the S-plane, S actually equals to 2. Okay? S equals to -2. The same goes for poles. We have S plus 5. So when you put it on the S-plane, it will have S equals to -5. Okay, so far any question? No? Okay, next one. So this is the, again, the same examples here. We have S plus 2, S over S plus 5. This is the system, GS. And let's say we have the input RS equals to 1 over S. So this is the step input 1 over S. So when we are trying to find the output, so remember the transfer function, we have GS. So I don't want to use GS because it's a system is GS. So let's say our transfer function TS is equals to this case is CS over RS. Okay, so the transfer function is CS over RS, output over input. So when we are trying to find the what we call it, the output, we can use CS over here. Basically, the CS is multiplication of RS to the system GS. So this is CS. So it is actually multiplication of RS and GS. Okay. So what we have is CS equals to RS GS. And we put in all the parameter or the system. RS is 1 over S. GS is S plus 2 over S plus 5. So you can find the response in time domain by the first one is you do the fraction here, the partial fraction. So you will find A over S plus B over S plus 5. So actually you have learned this in the previous lectures. So please refer to the previous lectures if you have any trouble understanding this. So from this, you can find the value of A, and then you can find the value of B. And finally, you take the inverse of Laplace transform. What you get is you get this form. Ct equals to 2 over 5 plus 3 over 5 exponential negative 5t. Okay? All right. So basically, when we put in the S-plane, we can put it the input pole. Basically, when you plot it on the S-plane, so the input pole is actually 1 over S. Okay, 1 over S, meaning that the S location is at 0. Okay, the S is at 0. That's why you have this S located at the 0 position on the S plane. Okay, and for the system 0, you have -2. So you put it on the S plane, -2. So it is on the real axis. And for the system pole, you have 1 over S plus 5, which when you put it on the S plane, you represent it by the X symbol, -5 over here. Okay, so the output is when we represent it in the frequency domain or S domain, we have is CS equals to negative 2.5 S plus 3/5 S plus 5. Done. Okay. All right. And then from this, you can also represent the fraction like this. And when we find the time in the time domain, you will have the form of 2/5 plus 3/5 exponential negative 5t. Okay, this output time response, we can divide, or we can classify the response into two type of response, which is the first one is forced response, and the second one is the natural response. Okay, the forced response is this. So the first one, okay, this is the forced response, and we have natural response, which is this one. Okay. All right. So the forced response is actually this one, is contributed by the input. It is contributed by the input into the system, and for this natural response is actually the response that is due to the system itself. So in this case, what is our input? We have RS. What is our system? Our system is GS. Okay. So the GS is actually, when we calculate, what we get is 3/5 exponential negative 5t. Okay, and then the input is actually is 2/5. There is no exponential in this expression, and you can see here this is a steady state response. The steady state response, meaning that the steady state response is when you plot it over t. Okay, so what you get is the response something like this. You have the first one is the transient response, and then you will get until time approaching infinity, you get the steady state response. So the steady state response is the value of steady state response is the forced response that is caused by the input. And then in between here, it is the transient response. So this transient response is caused by the system. Yeah? The system you have here determine the transient response. Okay. Okay. So next one, I will show you the effects of poles on the real axis. So when you put it, we have the poles. For example, we have the first one we have at poles at -2. Sorry, this is actually -1. So poles at -1. So when you plot impulse, you know, impulse, this impulse is actually the let's say, so this is t, this is the amplitude. So you give impulse input. Impulse is just one for example, so let's say the amplitude here is 1. Yeah, the amplitude here is 1. So you give 1 only at 1 second. And then you see what is the response of the input. You have the system G. Okay, you have the system G, and then you want to determine what is this the performance or the input, the output of the system due to impulse response. Okay? Due to the impulse response. So in this case, you have similarly you have CS equals to GS RS. Okay, RS. So now this input is impulse. So our GS now is 1 over S plus 1. Okay, for the blue line. Okay, when you give impulse input to the system GS, which equals to 1 over S plus 1, what happens is that it will decrease to 0. So you can see the blue line. It starts from at time equals to 0. At time equals to 0, the amplitude is 1. Okay, so as the time approaching 5 seconds, 1, 2, 3, 4, 5, it decays. It decays and approaching 0. Why? When you find the time response of this output, so you will get this expression, which is A exponential negative 1t. A exponential negative 1t. Okay, so if you calculate using your calculator, exponential negative t, you will get some value. You will get some value. So as you varies the value of t from 1, 2, 3, 4, 5, the value becomes lower and lower. The amplitude or the value of exponential negative t become lower and lower. And when we have the other system, we have the system, now we have negative 5. Okay, we change our system to negative 5. What we have here is now becomes S plus 5. So when we plot it, as we give the impulse response to the system 1 over S plus 5, you will get the red line. You will get the red line. So the red line here, you can see the rate of decays, the rate of change of the amplitude becomes faster as compared to the system 1 over S plus 1. And if we have another one pulled at negative 10 over here, the rate of change, the rate of decays become much faster as compared to the previous pole as at negative 5. So we can give conclusion to this observation. We can say that as the poles is located to the left of the S-plane, so the rate of decays becomes faster, meaning it reach the value of 0 faster if we put the poles location towards the left side of the S-plane. Any questions so far? This is a very important concept for you to understand. Any questions so far? No one. Okay. So I hope you understand this. So the essence of this is that the poles that is located to the far left to the S-plane decays faster as compared to the poles that is located near the origin. Origin means 0, near the origin. Okay. All right. Next. So I give you last time test signals to the input signal, step function, the impulse function. Basically, we have test input signals that actually that I want to stress on this lecture is we have three types of test input signals that is important for you to understand. The first one is a step input. The second one is the ramp, and the third one is parabolic. Okay, so test input signal for this step. So this is the step. So this is the ramp, and this is the parabolic. Okay, parabolic. So this is how you should remember the test signals. Okay, so the step function is actually RT equals to A for t greater than 0. So meaning that 0, t less than 0. So if you extend the plot, it becomes something like this. So at 0, okay, it becomes A. Yeah, and then it's constant A, regardless of the time. For the ramp function, however, the function is RT equals to AT, which is t greater than 0, and 0 for t less than 0. So if you extend something like this. And for the parabolic as well, AT square, which t for t greater than 0 and 0 for t less than 0. So something like this as well. Okay. So when you put it in S domain or frequency domain, you will have your step input is A over S, ramp is A over S squared, and for the parabolic is 2A over S cube, S power of 3. So let's say we say that unity step, unity ramp, unity parabolic. So what you have is we have 1 over S squared, 2 over S cube. Okay. All right. Next one. So for the step input, it is normally been used to test the speed of a system that is subjected to abrupt change of input. Okay, we want to set, we have a system GS, and we want to see what will happen when we give step input. So this is we use to see this the response if you give step input. So we will get what will happen is that we have forced response and we have the natural response. So we want to see the natural response of the system, because the forced response is actually the final output due to the input test signal. So in this case, it's test, it's a step. And then for the ramp, normally we use to test a system to follow a linearly changing input reference. And for the parabolic, normally been used to test a system to follow a rapidly changing input reference. So we will see later in these examples the use of the test input signals. Basically, I have explained these test input signals in the YouTube. So please refer to the YouTube and try to understand how I make the test input signals using the MATLAB and relate it to the theory that we will learn later. Okay. And then we come to the first order system. So we have first order system and we have second order system. For the first order system, let's say we have a system GS. Okay, we have A over S plus A. And if the input is a unit step, where Rs equals to 1 over S, what we have here is we have the output Cs equals to Rs multiplied by Gs equals to A over S plus A. So I hope everyone can understand how we get this expression. Okay, and then when we put it into a time domain, we take the inverse Laplace of the expression Cs. What we get is we get Cs equals to Cft plus Cnt, which equals to 1 minus exponential negative At. Okay, so the order of a system is defined as being the highest power of derivative in differential equation, or being the highest power of S in the denominator of the transfer function. So what it is said is, remember the last time we have for the mechanical system, for example, if we have something like A over S square M plus S B plus C. Okay, so this system is actually second order system because the highest power of the S is 2. So this is second order system. Okay, in this case we have GS. So the GS is A over S plus A. So the highest power of the transfer function GS here is 1. S power of 1. So we have the system is first order system. Okay. So a first order system only has S to the power of 1 in the denominator, while a second system has the highest power of S in the denominator of being 2. Okay, this is what I explained just now. And when you see the response here, 1 minus exponential negative 80, all right? So this is actually, we can classify them into, this is the forced response. This is the natural response. The forced response is due to the input being given to the system. And the natural response is actually the response of the system itself. A over S plus A. This is the response of the system itself. Any question? Okay, so you can see here, so this is the response characteristic that I have explained in the previous chapter, in the introduction chapter. This is the elevator response. We have the transient response, and we have the steady state response. Okay, so as the time approaching infinity, you can calculate the steady state error. Steady state error. What does it mean by the steady state error? For example, in this case, we want to go to the 4th floor. So this is 4th floor. You press the button 4 on the elevator. So what you expect is that you go to the 4th floor exactly. So the level of the elevator is the same as the floor. When you walk out from the elevator, it shouldn't be any difference between the floor and the elevator. It should be stopped on same level. Okay, so this is the input that we have given to the elevator. So the elevator have a transfer function. Let's say we have G, the G transfer function. So when we give, here is a step input 4, you can see the error by calculating where the elevator stopped at t approaching infinity. Okay, so if the elevator is in the same level to the floor, means that the steady state error equals to 0. There is no difference. But if, let's say, the elevator stops slightly below or slightly above the 4th floor, you will have some error. Okay, meaning that the given input minus the final output. That is the steady state error. So this is the given input. This is the final output of the system. So in the value here is actually the steady state error. Any question? Okay. All right. Now, a transient response specification for the first order system. All right. So we have a few transient response specification that we can define from the first order system. So we have a time constant, we have rise time, and we have settling time. So what is time constant? Time constant is the time for the exponential negative AT expression here to decay to 37% of its initial value. Or we can define it as the time it takes for the step response to rise 63% of its final value. Okay, let's say we have one minus exponential negative t, where t equals to 1, we have 0.63 to 1. So this is the time constant. For the rise time is the time for the waveform to go from 10% to 90% of its final value. And the settling time is the time for the response to reach and stays within 2% of its final value. So settling time also can usually by default is defined as 2%, but we can also define the settling time as 5%. So it depends on the questions. So whenever it's settling time, so by default it's 2%, unless stated settling time at 5%. Okay, so go back to the previous slide. We have here, when we put it in the plot here, the time constant is here. Okay, we have from 0 to reach 63% of final value. 63% of final value. Or in other words, it is the time taken to decrease to 30%, 37% of its initial value. So 37 plus 63 become 100. So it is two definition with the same concept. 63% is not here. It's actually over here. Okay. All right. So this is 37% decays to its initial value, or 63% from the final value. All right. So the rise time is the time taken to reach from 1%. So from 1%, from 10% to 90%, to 90%. So the time taken here is actually the rise time. Okay, and the settling time is the time taken for the system to stay within 2% of its final value. Because you see, when reaching the steady state, maybe it takes time to become stable, something like this. So in between, maybe it has some oscillation over here. So it oscillates before it reach the stable value. So it is actually so between plus minus 2%. Yeah? Plus minus 2%. Whether it oscillates plus positive, plus 2%, or it oscillates downwards, negative 2%. So it oscillates. So the settling time is the time taken to reach where the systems stays within 2% of its final value. Okay. Any question? Okay. All right. Okay, next slide. We have here the time constant tau is equals to 1 over A. Tau is equals to 1 over A. So when you see in the previous slide, we have, let's say we have the expression of output CT equals to 1 minus exponential negative AT. Okay, 1 minus exponential negative AT. So the time constant is defined as the time taken for it to decrease to 30%, 37% of its initial value. So here is actually when we want to find it. Okay, we put it, for example, is negative. Let's say this is A. So this is A. Let's say our T is 1 over A. Our T is 1 over A. So what we have is 1 minus exponential negative A. Negative 1. So try to calculate using your calculator. What you get is 1 minus, you will get is 0.632. So you will get about 0.37. So the time constant is actually this expression here, 1 over A. Okay. So what we have is for the time constant is tau equals to 1 over A. Okay? Tau equals to 1 over A. For the rise time, so this is from the calculation given. We can use the rise time is actually 2.2 over A, and the settling time is equals to 4 over A. For the rise time and for the settling time is they found it by numerically plot against the plot of the response here. So they calculate using the computer, and then you will get this expression for TR and for TS. Okay. Okay. Any questions so far? No? Okay, let's see some example here. So let's say we have our first order system here is GS equals to K over S plus A, where our step response is CS equals to K over S plus A. Okay, so S here comes from the input, 1 over S, step input. So when you find it, the partial fraction, what you get is you get K over A over S minus K over A over S plus A. And then you have been given this plot. You have been given this plot. So find the transfer function of this plot. Find the transfer function of this plot. Just given the plot here, the first order system plot, and then you need to find the transfer function. Okay, what we can do here is we can find the time constant over here. Okay, remember time constant tau equals to 1 over A. Tau equals to 1 over A. So from this expression, we can find, we know that the tau is actually the time taken to reach 63% of its final value. So for this is the final value, okay, final value. So we can, let's say the final value is 0.72. So we can find the final value multiplied by 0.63. What you get is you get berapa ni? 0.73 multiplied by 0.63. I think it's about 0.45. Let's say 0.45 over here. So from 0.5 you can extrapolate here, and then you can find the value of time. So here tau equals to 0.13 seconds. Okay, 0.13 seconds. All right. And then how to find the value of A? To find the value of A, we know that K over A is the final value. K over A is the final value. Okay? And A is actually, we can find the value of A using this expression. So we know that 1 over A is actually equal to tau. So our tau is 0.13 equals to 1 over A. So we can find the value of A. We can find the value of A. And then we can find the value of K, where K over A equals to 0.72. So we can find the value multiplied by A. Okay. So what you get is you get the value of K equals to 5.54. You get the value of A 7.7. So basically, this plot is actually when you plot it on the MATLAB, it is plot by this expression 5 over S plus 7 is actually. So see the resemblance of this the actual plot to the calculated plot, calculated transfer function. So 5.54 over S plus 7.7 is plus minus the same. 0.63 is actually comes from here. Remember the definition, this one. 63% to its final value, or 0.63 multiplied by its final value. So this is the 0.63 is the number that you multiply by the final value to find the time constant. Okay, Daya? Any other question? Okay. So this is the code to plot for MATLAB. So I hope you already see these slides, and then you watch the video that I have posted in YouTube, so you can relate this code to the output for the system, first order system. Okay, because next week you are going to have a lab 1. Saya post belum lab 1, not yet. So I will post lab 1 later on. So please see the lab sheet and then try to do it, and then actually, if you watch the YouTube video, I think you will have no problem understanding the lab. And then the lab is actually to enhance your understanding for the first order system and for the second order system uh, of the time response analysis. So try to do it and try to understand it. And then if you have any trouble, please always refer to me to find the clarification for any issues. Okay, so to recap, by now you should be able to define the poles and zeros of the transfer function given for the time response of a control system. And then you will be able to describe quantitatively the transient response of the first order system. So when we say about the transient response of the first order system, you must relate to the three characteristics, which is the first one is the time constant, and then the rise time as well as the settling time. Okay. Any questions? Okay, let's take a break, 5 minutes. So we will start at 11:55. In the meantime, please go back to the previous slides and see if you have any questions that you want to ask me.